I'm recording. I'll just give you an introduction. Hello everyone. Today Shong Wai will be presenting on modeling of Awatere Bridge, and he's PhD student under Liam. And Shong, you want to take over now?
Yeah. Okay, thanks. Thanks, Pavan.
Yeah.
Good morning, everyone. So today I'm going to present about the modeling of Awatere River Bridge in OpenSeesPy. This is a part of my PhD, which I'm doing. And so a little bit about the bridge description. So this bridge is located in Sydney, New Zealand, and it's constructed in 2007. The bridge has a length of 274 meters, and it has 10 spans, so it's about 27 meters each. And as you can see down here, there's a long section of the bridge, and over here at the left is just a photo of the bridge. And just to give you a little bit of context, where the bridge is located at. So this is a map of the north of the South Island. As you can see here, highlighted in red, that's the location of the Awatere River Bridge, located in the north of the South Island in State Highway 1. And it's crossing the Awatere River Bridge, the Awatere River. And so this is the bridge layout. As you can see here, there are some red dots here that are the locations of the accelerometers on the bridge. So on top here, above here, this is the plan view of the bridge, and below that's the elevation view. And we have some accelerometer at the top of the bridge pier. So at 3 locations, one at abutment A, and one at pier F at the middle of the bridge, and one at the near the end of the bridge in pier I. And also the 2 green dots represent the location of the south ground, north and south free field accelerometers located on the ground. So we have some records from these accelerometers, and we are going to we use these records to calibrate the model. So this is one of the abutment section and a pier section, just to give you an idea how the abutment and pier of the bridge looks like. And so on the left here, you can see the abutment. So the abutment consists of basically three columns and a pier cap. And you can see here there are 3 U-beams, which goes longitudinally across the bridge. And you can see here, down here, there are some elastomeric bearing located at the bottom of the U-beams. So these are located at the abutment. So this is a semi-integral bridge, and there are shear keys at the side, at both sides, at the end of the pier cap. And on the right here, we have a typical pier section. So it consists of 2 columns, pier cap, and also at the same, the U-beams, which goes longitudinally all the way along the bridge. And this, the width of the bridge is about 12 meters, and the height of the bridge is about 5 meters. And so the aim of this part of my PhD is actually to use recorded data from the accelerometers to calibrate the model in OpenSeesPy. So I was using the model response to calibrate the model. And I was looking for a change in model response based on 2 major earthquakes that has been recorded. So one is 2013 Lake Krasmera earthquake, and 2016 Kaikoura earthquake. So based on these 2 records, acceleration records, we can find some the response, can find the change in model response and how the bridge behave. And also we were looking at the sensitivity of the model response to different parameters, such as different pier stiffness, different soil stiffness, different bearing stiffness at the abutment, different linkage bar stiffness. And so this linkage bar is also located at the abutment, which I will show later, and also influence of scour at the bottom of the bridge. So the approach that was used was I was using a three-dimensional model, a 3D model. And for this part of my research, I'm using a linear elastic model to analyze, to do the analysis. And I was conducting model analysis for the bridge, mainly looking at the model response, the period, and the mode shape. So this is a diagram of the spine model of the bridge, just to give you an idea how I modeled the bridge. So basically the deck, I'm representing it using an elastic beam along the bridge longitudinally, and then for the abutments and piers, I'm modeling the main frame. So as you can see here, for every pier, okay, and so it's a three-dimensional and 6 degrees of freedom. And I was using elastic beam column elements for the modeling. So I have not gone into non-linear yet, and also using uniaxial elastic zero length elements for the spring elements for the soil, for the bearings, and linkage bars and shear keys. Okay, this is the model of my abutment. There is, as you can see here, there's a diaphragm at the front of the model in blue. And also, so this part, I was modeling it as a rigid element. Sorry, not rigid element, it's rigid, but it's an elastic column, elastic beam column with a high rigidity, which I will explain a little bit more later. And also the shear keys is located here, highlighted in red. So I'm also using uniaxial elastic spring material to model that. And on the left here is just the construction drawing. And on over here, there is an abutment section of the abutment. Over here, so I'm trying to show the linkage bar and elastomeric bearing and the diaphragm. So you can see here, this diaphragm is the same elastic beam column with high rigidity. And also I'm modeling this linkage bar here, which you can see here in the construction drawing, using a spring element, and also the elastomeric bearing as a spring element. And so this is the model that I use. So as you can see here, there is two types of elements, one in green and one in blue. So the green ones are actually I put here rigid element, but it's actually elastic beam column with high stiffness. So it's not the rigid element that is in OpenSees. It's just an elastic beam column with where I indicated here with high stiffness. So I've increased the I value and J value for the element. So just to make it stiff. And the blue ones are actually elastic beam columns with the properties obtained from the geometry of the element, and also the same for the piers, elastic beam column. And over here, there's just a 3D view, a simple 3D view of the abutment. So the green ones are the elastic beam column with high stiffness, and then the blue ones are the elastic beam column. And then, so over here, the red ones are actually the springs, so which are representing the elastomeric bearing and also the linkage bar. And also at the same place, I have some springs to represent the backfill for the soil. So this is indicated in brown. So it's actually just zero length. So I'm actually exaggerating it. So for visualization and so all these locations, these three locations are spring elements, zero length, uniaxial elastic elements, and then the top of the abutment is connected to the deck of the bridge, also by using elastic beam column across the bridge. So over here, my storage springs, I have 6 degrees of freedom, so which is at the bottom here. It's also zero length uniaxial elastic element in all 6 degrees of freedom in a translational and a rotational direction. And for my elastomeric bearing spring, over at the top here is also 6 degrees of freedom. And then I have backfill springs, 2 degrees of freedom, just representing the longitudinal and the transverse direction. And then my linkage bar is just 3 degrees of freedom, also longitudinal, transverse, and in the vertical direction. So all these are at these 3 locations, which are the zero length element springs. And these are just some photos of the damage that was captured after the 2013 and 2016 earthquakes. So as you can see here, there are some spalling and cracking at the top of the columns at the piers over here as well. And also at the bottom, spalling and cracking. So at these locations, I was reducing the stiffness of the elastic beam column. I was reducing the I value and J value by a factor just to model the damage by reducing the stiffness of the element. So I was reducing for the certain length. So about 1 meter, 1 to 1.5 meters. And also the factors, it depends on the severity of the damage. And then for the mass, I was using a mass per unit length. So I was I didn't assign mass separately, but I was using the mass per unit length component in the elastic beam column to capture the mass. So this is where I have the mass for my modal analysis. So I don't have any loads because for modal analysis it's not required for this part. So just mass. And then over here, this is just some of the results I plotted using Python. So generated using Python. This is the mode shape of the bridge, which was calibrated using the records. So I have 2 records here, 2013 earthquake and 2016 earthquake. And so these blue dots here, blue and red dots here are actually the recorded response. And the dotted lines are the recorded response. So, and over here is just the period of the bridge. And this is also some examples of the plots I plotted using Python in 3D. So these plots are showing the abutment, the response, the modal response of the abutments at both ends of the bridge. And over here, the blue one, the blue frame here is the abutment, and the red ones represents the modal displacement of the abutment. And so overall, all these plots are made so by myself, and also this one. So I extracted the points and then plotted using matplotlib in Python. And these are just some examples of the plots I made to show the influence of the different parameters on the bridge mode shape. So just to give you an idea, what was involved in this part of my PhD. And so over here we have stiffness, soil stiffness, and scour, different influence on the bridge mode shape. And over here just showing some different factors used and the different periods obtained. So just to summarize a little bit of my journey in OpenSeesPy, so some learning, some challenges, and some suggestions. So basically, I started learning OpenSees in Tickle. So that was the first language for OpenSees that I used. And then Pavan was the one who actually encouraged me to use OpenSeesPy. So because of various reasons. So how I learned, so Pavan was one of the main go-to person for me when I have questions. So other than that, I have learned from the examples in OpenSees PY, the structural and earthquake examples. So these are the examples that was very useful, I think, which is also the same as the OpenSees examples in Tickle. And but there might be slight differences in certain parts, but mostly are the same. And okay, the next thing is just going to talk a little bit about my background, because I was using, I started programming, learning Visual Basic as a programming language many years ago before using Python, and I was using MATLAB before Python. So for me, transitioning from this to Python to using Python was a bit of a challenge. I was a bit confused at first. I'm not sure about the others, because for me, I thought that at the time, programming is just, this is what programming is. But when I learned Python, it's a bit different. It's not just a language, but some thinking behind of the programming language. Like I have to, for example, I have to I have to relearn some variables, and then the way variables are defined, and then loops, how loops are written, even indentation. The indentation was not is not important, for example, in Visual Basic, but in Python it is. So I was using it differently. So when I use Python, it's a big change for me. But if you're starting with Python, I think it will be, for me, I think it will be easier for me if I've learned Python first before going into other programming language. So I think that Python is a good language to use to learn. It will be different if you learn Python first, I think. And just for I think most of you has started using OpenSees or programming before. So this is just some, if you have not used Python before, this might be something that is important, because programming might be something very new to you. So you might want to know exactly how to start with OpenSees. So basically you need to start with model definition.
Shong,
Yeah.
maybe you can also explain where you learned like coding and stuff to, like, if you want to, like, what sources did you use? Maybe that will also help others.
Yeah, sure. So I'll just finish this first. So I was using,
Sure. Sorry. Yeah.
no worries. So I was, so you start with model definition, nodes, elements, defining the nodes, then followed by defining the elements. So you have to go in this sequence, and then defining the mass and the loads and analysis, followed by the analysis, and then results and post-processing. So basically, this is the structure of programming or OpenSees. So Pawan was talking about what sources did I learn from. So mainly Coursera. I was watching some videos from in Coursera to learn Python, and also some websites. I can't remember the name. Is some websites related to Python. So these are the main websites that I use to learn. And also basically, if I have any problems, I'll just Google search the problem that I have, and normally there are someone else who have already encountered the problem, and I can just refer to how the problem is solved. And basically, over here for my bridge, I didn't just start with start to model the bridge directly, the whole bridge directly, but instead I started with a simple model. So and I developed the model progressively. So this is what I encourage everyone to do if you are just starting. And so if you have, I started with a simple model with hand calculation and compare it. So this is what I did. At first, I didn't know anything about OpenSees, and I wasn't very good about in modeling. And this is what I did. So a simple column, and also with a mass, lump mass, and just comparing the results in OpenSees with my calculations, and then just to understand how things works in OpenSees, and then moving on to a single peer, and then duplicating the peer, and then from there duplicated, continued progressively to develop the whole model, the whole bridge model. So it's not, I didn't just develop the whole bridge model directly. And basically I think that it's very important to check your results every time a change is made, for example, from this model to the next model. So you just want to make sure that what we change is correct, and also save it as a different file, because just in case something happens, you have something to go back to. You might get a lot of versions as you move along. But I think that is important, because sometimes something that works in the past, that in a simple model, you might think that, I mean, in the future, you might think that, oh, you might want to use this again. So, so that is a very good thing to have this file safe, I think. And so this is some of the processes that I use to develop my bridge model. So this is very important, especially if you have a very large model, whether it's a bridge or building. And also for me, I have springs as well, but I didn't just started with springs. I started with a fixed base model, so everything was fixed at first, just to get everything correct. And then I started, even the springs, I was doing it progressively. So the soil springs, and then the elastomeric bearing springs, and then the backfill soil springs, and then linkage bar springs. So these are the steps. So so it's important to develop the model progressively and make sure every step is correct, so that you get a correct result. If not, you will not know where goes wrong if you just do the whole thing at once. So it's harder to troubleshoot. And for me, it was I have some version and installation problem before. So sometimes you just need to make sure that the version that you use is compatible and is supported by OpenSeesPy. I mean the version of Python you use, whether it's Anaconda or something else. And also make sure that your your version is updated. And you can check the OpenSeesPy website to make sure that the version is correct. And sometimes I have to upgrade it, and I have to uninstall it and install a previous version of the Python and in previous version of the Anaconda, just to make sure that it works. And basically, this was what mentioned by Pawan in the last meeting. So using a dictionary for storing your variables, things like your nodes, elements, and even your output, so that you can use it the next time for plotting without running your model again, which might take time. So I'm actually also trying to do this, because I was doing exporting using Excel, exporting to an Excel format, which might take more time. So I think this is a better way to use. And also some errors that I encountered before. So, okay, I was having this problem because I thought that I was having a problem where I was not getting reactions before. I was just doing a simple analysis, and I thought that maybe it's my model problem I couldn't find, but sometimes it's just a very simple problem. Like, for example, the reaction was not called first before the no reaction command. So this kind of, it is a very small thing, but so it happened to me, but maybe is something that you want to look at. And so sometimes I have some extra nodes I define which is not connected, and it gives me errors. So just make sure that you have all the nodes connected, and you don't have a node flying outside of the model. And
Shong, one thing here,
yeah, sure.
sorry. What kind of errors do you get like when the nodes are not connected? Can you just tell me that?
I can't remember the error.
So,
It's
okay,
something like,
singular matrix error?
yeah, something like that.
Yeah, yeah, I just wanted to tell that. That's
Yeah,
it. Just
yeah, it's
because
singular matrix error. So,
because like most of us will not know why that is coming singular matrix, because it's not connected to it's not going to say directly node not connected, it's going to display
yeah,
singular matrix error. And one other case when that error might pop is when you have two nodes very close to each other. Like for example, all your nodes are like 100 apart, but for example two nodes are like 0.1 or for some reason you have nodes, you are dividing the elements into 10 divisions, and Python does like some weird divisions. Like sometimes you get like 99.09999 and there is another node at 100. So if you have two nodes like that, then also that kind of error pops out. Just telling, since
yeah.
that's
So
that's a very good
this,
point actually.
yeah. So these errors actually. OpenSeesPy doesn't tell you that whether
Yes,
this is the error. So
yes.
so it's very important to know that
To
to think about
correlate,
that.
yeah.
And it doesn't tell you exactly whether there's a node not connected or which node is not connected. So you need to make sure, especially you have a lot of nodes, a very big
True,
model.
true, yeah.
So you need to make sure that you know where your nodes are and what you are doing very clearly, because sometimes you might not be able to visualize every single detail.
True.
Um, just need to make sure that, take note of that. And also, like for example, for me, sometimes the zero length elements are not zero length. So for this one, the program actually tells you that this element doesn't have a zero length. So I have to go back and check which element it is. But for the first two, it doesn't tell me. So it's just I just learned along the way that okay, this is the problem if there's a singular matrix error coming up. And if I don't get a node reaction, it probably is not because of the model, but it could be. And it could be also because of this error. You have this, you didn't call this command before calling the node reaction command. So these are just some examples of the errors that you want to take note of. And also about node and numbering, node and element numbering. So you might want to think about the possibility of both increasing and reducing nodes in the future, because this might affect your how you want to number, or how you want to number your nodes. Because when you add your nodes, you might need to assign a different number. So you want to allocate enough numbers, or for example, you want to use a way, for example, like Pavan suggested, using a grid system or something different to mitigate this error, because it might be confusing for you if you didn't manage the node numbering well, especially when you need to refer to where the error is, or if you want to plot the model output in the future. And especially you have a big model and you have many kinds of output you want to plot. So and looping. So I think it's very important to use loops wherever you can. Just try to avoid repetition, and also some plotting mistakes that I experienced. So I was getting the wrong nodes to plot because I was writing my own code to plot, for example, the model response that I showed you just now. So before I knew that it was a wrong node, I thought that there was some problem with my model. Maybe my model was wrong, or something was not making sense in my model. And then I was looking at the problem, but in the end, I realized that that was not a problem, but it's just the problem. There's nothing wrong with my model, but it's actually I actually picked the wrong nodes, like just three wrong nodes out of many nodes that gave me a weird response that I thought that, okay, something is wrong with my model, or maybe this is the response that I should expect. So this might be something that you want to take note of also. So how to avoid this, like to getting the wrong nodes. So I think one way is to actually really segmentize the nodes that you want to use in a model. Like for example, if you have, for example, for the bridge, the abutment might be one segment of nodes. Maybe you want to use certain numbering for that, or certain grid numbers for that. Depends on your method. So you need to come up with a very planned and organized way to organize your nodes. So again, especially if you have a very big model, and yeah, also that's also to make sure that you have room for increase, or if you need to reduce your nodes in the future in your model. And so this over here, this is just a link. I'm not sure if you know, but maybe some of you know. This is just a link that I used before to get some resources to learn OpenSees. So these are some workshops, training workshops back in 2017, a few years ago. So this is in Canterbury's wikis page, and so there are some files there. The examples are quite similar to the Tickle and the OpenSeesPy files, but there are a little bit more annotations there, which might help you to understand some processes better, especially if you are just starting out. So you might want to have a look at it. And our future works, these are just some, so that was what I was talking about is linear analysis, an elastic model. So basically I'm going to continue with ground motion analysis and nonlinear analysis. So this is what I'm going to do next. So I think that's all, yeah.
And what can you explain what you're doing here, please?
Over here, just a moment. Over here, oh, this is just some outputs. I was matching the recorded response and and the moded response. So this is the time history of the bridge, at the middle of the bridge, on top of the pier.
During which earthquakes, or what are the time history from? Can you
this is from 2016, Kaikoura earthquake.
Okay.
So
your model is going to, so what kind of changes are you planning to do to your existing model? Like you are going to change the elastic elements to fiber sections. Apart from that, are you planning to do any other changes?
So basically,
I mean, you can just give like what
yeah,
you have.
I'm just changing some elastic to fiber to I haven't decided yet, so it's going to be non-linear, and going to make the hinge at the top of the bottom of the column,
Okay.
and to simulate the damage.
Okay. And you'll be running in uniform excitation, right? Like all those models.
Yeah, at this point of time, it's uniform excitation.
And okay, cool.
Is there any questions?
Yeah,
Thank you, Tom. Yeah. Go ahead, Claire.
I have a question. I guess, well, mostly my question is about, practices when you make your OpenSeesPy code, because I don't know, but correct me if I'm wrong, but I think most of us are starting out. So actually, first of all, I want to thank Shong for his presentation, because I think it's very useful, especially for people who are just starting out working with OpenSeesPy. One of my questions is, you were talking a lot about setting up your nodes, right?
Yes.
What I've been doing actually is sometimes it's kind of confusing especially when you have too many nodes. What I do is I have a drawing, I have a drawing in, well, I just use Adobe Illustrator, but I know that, even just a drawing on a paper would suffice. Do you do that as well? And maybe Pavan can chip in to my question as well.
So,
For me,
so,
okay.
so go ahead, Sean. I'll answer after you.
For me, I was starting up with AutoCAD. I was also I was sketching at first, and then I was using AutoCAD after that. But maybe Pavan have a better suggestion.
So I did with a pen and paper initially to set up like my initial idea. So like when I was making the grid, I was trying to draw the three-dimensional grid and then number everything like by hand so that I get a better feel. Like once I know like, okay, this is how the flow works, and I'm confident that I can extend that system to all the things I will be encountering. For example, one of the most interesting thing, I mean, which I didn't mention last time, is this will this is one of the critical factor which turned out to be a critical factor which not many of us know. So the number of digits actually you can use in OpenSees numbering, there is a limit on it. So it's 2 power 32 minus 1 is the biggest number you can use as a number. So that turns out to be like something like 9 digit or 10 digit number. With, and the some 2 after 10 9 more digits, okay, because like that was restricting me to use like 4 digits for each grid, like first 4 digits for x, next 4 digits for y, next 4 digits for z, because it was becoming 12 digits, so I had to stick to 3 digits each. So
Right.
so these, I mean, I was like using 4 or 5. It was like saying no, no, no. I didn't realize like why it was saying no, but then it was like, oh, it has a limit actually on the biggest number you can use. It's on the bit size or something. It's more like computer science related stuff. So there are going to be other constraints as well. So which is going to govern what you are going to use. And the other thing which was is like I used all positive numbers for my regular nodes, and I was using a lot of slave nodes because for I was modeling the PY curves, so I had to use zero nodes, right? So like so what I was doing is for each node I had like I mean in X direction, Y direction, and Z direction soil spring. So I created 3 additional nodes for a particular file node. So what I did is like if I was keeping the same positive, it was confusing. So I kept a negative number. So the other thing is you can actually number your nodes using negative numbers. So which is a powerful thing because then all the positive nodes are normal nodes and all the negative nodes are slave nodes for me, or like the zero nodes kind of thing. So it was clear for me those. So those are the things which helped me to optimize my uh, grid system, which I was coming up. Maybe like these things will help you also like to factor in and see like okay how to number it.
Yeah. Well, to be honest, so I'm making a building model,
Okay.
and the thing with my code is that I want it to be scalable, meaning
Yes.
that if I extend the number of bays
Yes.
or if I increase the number of stories, then I just have to, change 1 or 2 variables, and then it will do that on
Yes.
its own.
Yes.
And
Yes.
that's why it's taking me quite a while to
So
simply, just form my elements and then add to that the zero length elements and all that, then it kind of takes a while. And
yes.
so that's why I have, I guess an illustration of how my grids look like so that it's easier for me to
So
to understand what's going on, because sometimes it gets a little bit difficult.
yes.
And
No.
I
No.
don't know if that's also something that other people want to see.
Yeah. I mean, if
Yeah,
I
I
can.
know.
Yeah, you
Yeah.
know that's a very important point, and it was like as I showed you last time, like I had to encounter different bridges and I wanted to use one code, and every time the bridge was adding, the requirements was changing, so I had to change it. So it's actually good to do the think of, I mean, as a student, I feel that, but as a supervisor, the supervisor might think it's waste of time sometimes, because if you're just going to do work on one building, then it's like not, I don't know, that depends. But if you're going to model like 2 or 3 different buildings, then I think it's actually, it doesn't take too much time once you figure out, like once you get the idea, it's just implementing will, maybe it's like one extra or month here, but when you are actually doing it manually, you will invest more than that time, like when, or for post processing, or for this, where you are figuring out, oh, which node, how to do this and all that at later stage. I mean, I personally think that, but yeah, I think it's good to do that way. Struggle now and enjoy it later. You can actually focus on things important.
Yeah, sounds good.
I mean, if more people wants to know that, I can actually go over like the grid system, how I did and all that stuff in more in detail. That way, maybe it will help, like, because it was not easy to come up with, as I told you, like there are a lot of other constraints. I just told you 1 or 2 constraints, but there are like going to be a lot more constraints when you're coming with a system like that.
Yep, sounds good. Yeah, I think I was just thinking that's one of the things we can start with in these meetings, because
Okay, cool.
I have the impression that a lot of us are just starting out, right?
Yeah.
Yeah, no? Okay, yeah, sounds cool. Actually, yeah, I mean, well, some people can ask questions now. I'll make my suggestions later.
I will talk to Max about it, and I think like he was also up for it, like last time when I talked to him. But like I'll just discuss it. Today he's not there; he has another meeting. But like once I'll just discuss with him, and like that's a very good direction to go in, I think.
Yeah. Yeah, I also have a few suggestions when it comes to OpenSeesPy, because apart from some people who are just starting out with OpenSeesPy, there are also people who moved from Tickle to Python.
Yeah.
And I think I was just wondering if it's going to be useful if we had a session on good coding practices, because, well, so I've been using Python for a long time now, and there's this, I don't know if you know about pip 8, the style guide for Python code.
Yeah.
And
And
it's
that's
really
best practices, right?
a pip 8, it's called pip 8.
Yeah. I mean, where they explain you what are the best practices to write code, right? Yeah. Okay.
Yeah, I think
Cool.
I don't know if that's something that people are interested in, but if it is, then maybe we can do that as well. And also how to use Git. I think Git is also useful.
I mean, you can. That would be good. I think. I mean, if later, yeah, these are the things. Good suggestions. I'll add that, and then I will come back if that's fine.
Yep. Thanks, Pavan. Thanks,
Sure.
Shong.
No worries, thanks.
Any other questions from anyone or suggestions from anyone? If no, I can ask some song like related to modeling.
Yeah.
So you go. Can you go to the starting of the presentation? I'll just want to highlight some stuff where like I think is useful for everyone to keep an eye on, maybe, or like some of them is like questions, some of them are like points to highlight.
Sure.
So you said like you're using elastic elements, and when you're modeling the damage, you're using reduced I values in top 1 or 1.5 meter, right? How
Yeah.
did you come up with that 1 or 1.5 meter value?
For that, I didn't, it's just an estimate.
I mean, based on like the images, or like did you get that from like the figures? Or, like,
No, it was because the image, I didn't have all the image, so that was just an estimation. Yeah, just a rough estimation.
Okay. I mean, did you calculate the hinge length and then you, based on that, you reduced or like how?
No, no.
Okay, okay. I was just curious how.
Yes, I understand that. But
Okay.
I think, yeah, it's if like for because for this bridge, for my case, the structural, I found out that the structural damage is not really governing. So I was not looking at it at a very um, uh, how do I say, in a, I was just looking at it in a very high level way. It's,
Okay. Okay. Yeah. Uh, and when you were using rigid elements and elements, elastic elements with high E values, what was
yeah,
the difference you noticed? I mean,
rigid elements and elastic beam
yeah,
column wave.
yes. So for the diaphragm elements, you used, you said like you were using high element, elastic elements with high E values, right?
Yeah, yeah, I get what
And
you're asking.
yeah,
Uh,
you must have noticed change in the periods or mode shapes or
Actually, there
something.
was a big difference. And for my
Sorry?
bridge, there wasn't a big difference for my bridge.
Okay, okay,
I didn't really see any noticeable difference, but I know that there is a difference because it's a
okay,
rigid element is not entirely rigid.
okay.
Um,
No, rigid element is entirely rigid,
I mean,
not,
I mean the elastic. Sorry,
yeah,
the
yeah.
elastic. Yeah, it's
Okay,
not.
cool.
Yeah.
Yeah, I mean, I just want, because like I noticed in my models, like when
Mhm.
I was changing from rigid to elements with high values, there was change in the periods. So that's why I was like checking if you also experienced the same thing.
No, I can't remember whether I looked particularly at it, but I know there's a difference.
Okay, cool. And that's and linkage to,
Linkage,
so,
linkage
so
bar.
so when you said like the mass, this is another, sorry, that you answered at later stage. Mass
Mhm.
here, there is another thing which a lot of people will miss. We had a discussion, so like,
Yeah.
so when you're using mass like this, distributing your mass like this, how is it calculated in the open? How does OpenSees calculate the mass distribution?
So this mass is a distributed mass. So this is the mass per unit length of the element, whether it's a column or beam.
Yes,
So when you in OpenSees, when it calculates it, it's actually lumping a mass at the end of the
yes,
element as well.
okay,
So that's
yeah,
how OpenSees do it.
yes. I mean that's an important thing because like when we use this, we assume that it's actually calculating distributed. So
Yeah.
just I wanted to highlight that one. And and one thing, Sean, when you go to your results in the middle tier, so, yes, why was the, I mean, change in the response from abutment A to abutment A? Why is that difference too much? Like, what were the reasons you noticed? The reasons for that?
Mainly the soil.
Okay, because the soil
There was
profile
a,
is changed. Okay,
yeah, it's not so much of the structure, but more of the soil.
okay, cool. And and in the abutment figure, can you go back once to the abutment figure?
This one?
Next, yeah, this one is fine. You for the middle tier, middle column, you have two, like a spring, two springs there,
Mm-hmm.
and for the corner ones, you have only one. I mean, can you explain why you did that?
You mean this one?
Yes, yes.
Okay, this is actually just for the backfill in the transverse direction.
Okay,
Um, because um,
proceed.
the the response actually all the other springs are in all the location, but that I'm actually is just I'm just visualizing it. This is just to represent the backfill, but actually it exists. Like over here, there is a transverse for the elastomeric, for
Yes.
the linkage bar, for the
Okay.
um, shear keys as well.
So you are summing up all the transfer direction stiffness and you're lumping it in one stream, right? There.
But that's just for the backfill.
Okay. And is that unidirectional or like what I mean is it taking only compression or like compression and tension both?
Compression and tension.
Yeah. I just wanted to highlight that part because
Yeah,
it's
it's
important.
taking both compression and tension.
Okay. And how did you, so from 2013 to 2016, did you make any changes to the soil as well in the model? You said like you reduced the stiffness of the column, right?
Yes, yes. Yes, I
Okay.
didn't mention that. So I did change the soil as well because and I found that there was a change in the soil profile, the soil stiffness.
Okay, cool.
Yeah,
So that's also the reason why the things are changing there, right?
but what was changing?
Soil. Because of the soil change also was one of the reasons to change the mold shape, right?
Yes, and that's the main reason, one of the main reason.
Okay, okay.
Shong, to add to that,
Yeah.
is that the main reason why the slab or deck at F position has almost all the different responses coinciding?
Uh,
The variability of soil.
Actually, no, because over here, you can't compare the 2013 and 2016. So you can't compare the blue and red one um, based on this figure. This is just to show this because this is, how do I say? This is a normalized. This is a normalized mode shape. So what I'm concerned about in this figure is the shape, not the relative difference between the two.
That's important. Yeah.
Okay.
Okay.
Yeah, you can't compare it because it's different.
Yeah.
Oh, yes, of course.
Yeah,
Thank you.
no worries.
Anyone has any other questions? I'm done with my questions.
Okay, thanks. Any other questions?
Looks like no other question. And just is anyone else if anyone else is interested in presenting, please let us know. And mostly next presentation we will have from one of external guys. His name is Nasser. It will be on September 11th. So yeah, and if for future presentations, if anyone is interested, it need not be like end-to-end presentation. You can just come up with okay, this is my project and this is what I am planning to do, and like you can have like inputs from others. That's also fine because like it's not like you have a finished product and you're presenting here. You can just try to get inputs from what you're doing as well. Okay, if no one has any questions, then
I
we
think
can
that's
end
about
it.
it.
Yeah. Thanks a lot, Shong, for the presentation. It
Thank you,
was really
Pawan. Thank you,
nice.
everyone.
It was really nice, and you covered a lot of
Oh,
important points today. And
good to
hopefully,
know that.
it will help other students who are who have started doing stuff.
Yeah, definitely. I hope it was helpful.
Thank you, Shong. Thank you, Pavan. Shong, I think
Thank
that
you.
was very useful.
Thank you,
That was
Thank
a
you
good
everyone.
for telling me.
presentation.